In this video, we will examine a bucket theory and energy exchanging of LC as well as resonance. For inductors and capacitors, they are both energy storage components that we can think of as buckets. What matters is the capacity of the bucket and how it behaves when receiving or releasing energy. An inductor has an impedance of j omega L or a reactance of omega L. Its energy storage capacity is equal to I squared times XL. On the other hand, a capacitor has an impedance of 1 over j omega C, or alternatively, it can be expressed as negative j times 1 over omega C. Its energy storage capacity is equal to I squared times XC. We can use a diagram to illustrate the relationship between inductance and capacitance with respect to frequency. The reactance of an inductor increases proportionally with the frequency, whereas the capacitive reactance of a capacitor decreases with the frequency due to its relationship to 1 over omega C, which is inversely proportional to frequency. These two lines, one rising and the other falling, will intersect at a certain frequency, known as the crossover frequency. At the crossover frequency omega 0, the reactance of the inductor is as large as that of the capacitor. Now let's consider a series LC circuit. As the frequency increases, the capacitor's bucket, that is its reactance, becomes smaller, whereas the inductor's bucket becomes larger. At the crossover frequency, the two buckets will be of equal size. If we examine this circuit at a particular frequency higher than omega 0, then the inductor's bucket will be larger than the capacitor's bucket. In this scenario, the series LC circuit will be inductive. To help illustrate energy transfer, let's use an analogy of a relay race. Imagine a series LC circuit with a signal source on the left and a load on the right. When we connect the source to the circuit, the signal travels through the series LC circuit and ultimately reaches the load. Initially, we assume that both the inductor and the capacitor buckets are empty. During the first half cycle, the inductor receives energy while the capacitor discharges. In the next half cycle, the inductor begins to release its energy to the next capacitor, which simultaneously receives energy. However, since the inductor's bucket is larger than the capacitor's, the capacitor will eventually overflow. Where does the excess energy go? It returns to the source. This is because when the capacitor receives energy, it cannot release energy at the same time. In this half cycle, any excess energy cannot be released to the load and must return to the source. When the capacitor becomes fully charged, any remaining energy is virtual work. In the next half cycle, the inductor once again receives energy while the capacitor simultaneously releases energy to the load. The amount of energy the capacitor releases to the load is the real work. When the operating frequency is lower than omega 0, the inductor's bucket will be smaller than the capacitor's bucket. In this case, the series LC circuit will be capacitive at that frequency. If we have a small inductive bucket in series with a large capacitive bucket, during the first half cycle, the inductor receives energy until it's full. In the next half cycle, when the inductor releases energy, the capacitor receives energy from the inductor, but only up to the maximum amount of energy that the inductor can store. During the next half cycle, the inductor receives energy from the source once again, while the capacitor simultaneously releases energy to the load. Now, what happens if we operate at precisely the same frequency as the crossover frequency, meaning that the two buckets are the same size? During the next half cycle after initialized, the inductor begins to release its energy to the next capacitor, which receives exactly the same amount of energy that the inductor has stored with no waste. Everything is perfectly balanced, and this is known as the state of resonance, where the inductor and capacitor are in equilibrium. When the resonance occurs, the two buckets behave as if they are transparent. The energy supplied by the source is delivered to the load without loss. It's as if these two components are short-circuited and the signal flows directly to the load through them. In a parallel LC circuit, since the inductor and capacitor are connected in parallel, they have the same voltage across, so it is less like a relay. During resonance, the two buckets exchange energy equivalently as if they are playing with each other and not concerning themselves with the outside world. At this point, they no longer need any energy from the source, and the circuit appears to be open, since no additional energy needs to be added to the tiny and self-contained system. We can gain some insights from this. To achieve resonance, we need two buckets, that is, the inductor and capacitor, with one bucket receiving energy while the other releases energy. Without these conditions, resonance cannot occur. The second insight we can gain from this is that during resonance, the inductor and capacitor exchange energy continuously. However, when a load is connected, the circuit experiences resistance and consumption, including internal resistance from the power supply. If we can remove the resistance of the source and load, the circuit will behave as if only the inductor and capacitor are present. In the absence of losses, they can exchange energy indefinitely without any source, resulting in oscillation. The question is, how do we take this resistance out of the circuit? To eliminate the resistance in the circuit, we need to generate negative resistance, which is possible using an active component such as a transistor. This is why oscillators typically incorporate transistors in their circuits. Another insight is that if we observe ringing in the circuit, it cannot be a first-order circuit, since a first-order circuit cannot exhibit ringing. Finally, in designing a resonator, we are essentially designing a filter. In the real world, all passive components exhibit resonance since they are not ideal and have some level of resistance, inductance, and capacitance. As a result, RLC components may resonate at certain frequencies.